Hi, in this video, we'll be discussing how to create the magnitude plot given a transfer function, as seen on the screen. The top part, the numerator of the transfer function, allows us to find the zeros, and the bottom part of the transfer function allows us to find the poles. In the next step, we will show you how to convert to a format that can be more easily graphed to find a gain.
So now in the next step, what we did is we factored out coefficients to assist us in obtaining a value, which will help us in finding our gain later. So from the top where the zeros are, we factored out a 20 right here and a 200 right here. On the bottom where the poles are, we factored out a 10 twice, therefore 100, and a 500, which was factored out as shown on all of these were factored out as shown on the left. And this value right here will assist us later in finding our gain. So all I've done here is I've just simplified the first coefficient right here on the left, which will be used to find our gain later. So 20 times 200 over 100 times 500 simplifies to 4,000 over 50,000, and then this whole term simplifies into 2 over 25.
Our next step is to write the magnitude equation of our transfer function, of our simplified transfer function. Because the magnitude plot is plotted on a decimal scale, we want to take the 20 log 10 of each term in our simplified transfer function. Now this term is squared in our transfer function, as you can see, but we still put it in a 20 log 10 format. Since it's squared, there's just two 20s, aka a 40. Our zeros result in an increase in slope of 20 decibels per decade on the magnitude plot, which is why you see pluses in front of the terms that resulted from the zeros on top of our transfer function. Our poles from our simplified transfer function result in a decrease of 20 decibels per decade slope in our magnitude plot, which is why you see minuses in front of them on the magnitude equation.
So shown below is just a summary of what was just stated, so you can play or pause it at your own convenience. The first term is the gain, and then here the notation I've used, the plus indicates an increase in slope of 20 decibels per decade, and the negative indicates a decrease in slope of 20 decibels per decade, while the number itself indicates where that change will occur in terms of radians per second.
In this step, we've plotted the magnitude plot, but we're going to go through each step. On this axis right here, we have our decibels listed by numbers, and on the x-axis we have our radians per second values, which is on a log scale. And so our first step is that you saw that our gain was negative 21.938 decibels. That corresponds to this value on this axis, and it's gonna exist all the way until our first radians per second value, which is 10. Now at 10, we have two poles, negative 10 and negative 10, because they were squared, and so from there we're going to have a decrease in slope of negative 40 decibels per decade. That decrease in slope is going to persist all the way until our next prompt, 20 radians per second, There we have a 0, so it's going to cause an increase in slope of 20 decibels per decade. We were just at a slope of negative 40 decibels per decade, and when we add that 20 decibels per decade, it's going to result in negative 20 overall slope. That's going to persist until our next radians per second value, which so happens to be 200. It's another 0, so we're going to have another increase in slope. Now remember, we were at negative 20 decibels per decade. Once we hit 200 and have another increase of positive 20 decibels per decade, our response is going to flatline at 0 decibels per decade until 500 radians per second. That's our final radians per second value, and since it's a pole, we're going to have a decrease of 20 decibels per decade slope. And since it's our last one, it's just going to keep going down at negative 20 decibels per decade forever.
So now we're just going to do a quick analysis of what type of filter this is. So it's important to know a few things. everything above the x-axis is passing and everything below the x-axis is deemed as not passing. So because here every value in our magnitude plot is below the x-axis, this would be classified as a no-pass filter. So just to show you some other examples of things you might see in class, this is what a high-pass filter would look like, and these are just arbitrary axes. This is a low-pass, this is what a bandpass would look like, and this is what a notch, or also known as a band-stop filter, would look like. Thank you so much for watching.
This concludes our video. Good luck on your exam.